Hey guys, we're going to continue talking about Newton's method today, 3.8. So we just have a couple quick examples to go over, not too many, but these are continuing your notes from lesson 3.8. So remember with Newton's method, generally as we get better approximations, as we go through all the different iterations of Newton's method, the sequence converges, okay, so it gets closer and closer to the actual zero. But it doesn't always converge. For example, if the derivative is 0 at any point, the method will fail, although you can often overcome that problem by picking a different starting value. So I have a picture here of one that happens to fail. So you can see here's our actual 0 that we're trying to get. So if we started here with x1, we've found the derivative and found where it crossed, which is what Newton's method does. Here's our x2. So then we find the slope down here, and notice that when we solve that one, we end up with our x3 way over here. So like I said, sometimes Newton's method doesn't work, and it'll get you further away. Sometimes you can correct that by just picking a different starting value. Another way that Newton's method can fail is if the function is not differentiable at a particular point. So we have a function here, f of x equals x to the 1/3 power, and I've got that on Desmos here. So you can see right here at 0, where its 0 is, it's not differentiable. It has a vertical tangent at that point, so you can't differentiate there. So we already know ahead of time this is going to be a problem. So we want to show that Newton's method fails to converge, and they've given us a starting point. So I'm just going to walk you through this one quick. So before we do Newton's method, we're going to need the derivative, which I already calculated here, 1/3 x to the negative 2/3. And we'll start filling in our table. So we said x1 is 0.1. And then when we plug into our calculator f of xn over the derivative at xn, we get 0.3. And then when we subtract those, negative 0.2. Okay, so this becomes our new xn for our next iteration. And I know I'm going through these kind of fast. You obviously can do this on your calculator. So when we do f of xn divided by the derivative of f at xn, let's see, negative 0.6. And when we subtract those two, we get 0.4. So for our next iteration, 0.4 is our starting value. Here we get 1.2, and when we subtract those, negative 0.8, and that becomes our new starting value, negative 0.8. Here, negative 2.4, and 1.6. Now, if we were to continue on, that 1.6 would become our new starting value. But let's look and see what's happening here. Remember, our approximations are supposed to be getting closer to the root. But notice we started at 0.1, and then negative 0.2, and then 0.4, and then negative 0.8. So not only are they alternating back and forth between positive and negative, they're getting further away. Remember, when we looked at Desmos, our actual 0 is at 0, right here. So, and this is happening because it is not differentiable at its 0. So, just so you know, Newton's method doesn't always work for various reasons. Now, all these calculations are kind of obnoxious, so I want to take us back to example number 1. And we did this yesterday in our notes, and we did the whole table thing. We want to calculate 3 iterations of Newton's method to approximate the 0 of f of x equals x squared minus 2, using x1 is 1. You can do this with your TI calculator. It takes a little bit of programming, but the next video, it's a YouTube video and it's short, it'll show you how to do that. And it is pretty straightforward, and you might hate me a little bit for not teaching you this yesterday, but that's okay, I can deal with that. So watch that, and then when you do your homework tonight, feel free to use your calculator to apply Newton's method.